So last time we talked about the category of monoids with monoid homomorphisms between them. Today we're going to look at a couple of other categories that we've seen before, but we'll see how to implement them. So here, I'm defining a contract that expects a pair of numbers. Call x the first one and y the second one. And we want x to be less than or equal to y. So if x is greater than y, we throw an exception, otherwise we return the pair. So there's a contract for pairs of numbers where the first one, x, is less than the second one, y. Now we can turn this into a category by defining a hom functor for it. It takes in two parameters, just like the other hom functors, checks that they are both less than or equals, these pairs where the first one is less than or equal to the second one. Then it asks for a middle one. Then it checks to see that the bigger number in before is equal to the smaller number in middle. If not, throws an exception. Again, it checks to see if the bigger number in middle equals the smaller number in after. If not, it throws an exception. Then it takes the smallest number of before and the largest number of after. Well, what does that mean? Well, this is just the transitive property of the less than or equal sign. So here, if I have 3 is less than 5, and 7 is less than, 3 is less than or equal to 5, 7 is less than or equal to 9, then I can compose these things together. Let me see if I can type this using this fancy thing. 3 so that's the first part. And then the middle part is less than or equal to 7. And then 7 is less than or equal to 9. So when we compose these three less than or equal to's, we get 3 is less than or equal to 9. So when we do this console.log, we should get 3 and 9, right? Because before 0, that's this thing, and after 1 is that one. When we run it, 3, 9. Great. So now we have the ability to compose these less than or equal to statements. Now the identity less than or equal to is just a pair XX, because x is of course less than or equal to itself. Here's another one. Div. As before, it's a pair. This time we want natural numbers. Then we look at the fractional part, and we divide this should be y divided by x. So if y divided by x has a 0 remainder, all is good, otherwise we throw an exception. So this div accepts things like 2, 4, because 2 divides 4. 2 is a factor of 4. 4 divided by 2 has 0 remainder. Okay. Then we can compose these, exactly the same logic. And then here, oops, comment that one out. Here, we're saying 3 divides 6 24 divides 96, and 6 divides 24, therefore 3 divides 24. And let's see if that works. Three divides 96. Oh, sorry. 3 divides 96. Yep. So that works. So anytime you can define a contract for something, you can, well, not anytime, but many times you can define a contract for something, and then you can define a HOM specific to it that isn't necessarily guarded functions. So in particular, any partial order. The order using less than or equal to, that was obvious. That was a total order. Here we have a partial order from divisibility. So in this sense, 3 is less than 6 in the order. And 2 is less than 6. But 5 is not necessarily less than or equal to 6. Neither is 6 less than or equal to 5. It's a partial order. Because neither one divides the other, you can't compare them. But when you can compare, you can compose them together. And that's what this is saying. So any partial order can be turned into a category. In fact, it's a category where there is at most one morphism between any two objects. That's why when we were composing them, all we had to do was check that the source and target of the things we were composing matched up. We didn't have to do anything with it, just check that it matched. So in any partial order, you can use this sort of pattern that we used for div and for less than or equal, and get a category.